Okay, thank you. So, all right, so we continue with with measures on. Right, so I've been talking about how to normalize measures, and so I've defined a measure on G, and now I have to define the measure on T, right? Because in the orbits I have the quotient measure. So the measure on T is a bit more interesting. So right, so this is what is the point is what is this dt that we're quotienting by, and so the group G kind of, so in order to define a differential form, we first kind of need good local coordinates. I mean, T is an affine variety, so we just need kind of a good coordinate system. And then you think about it and realize that there's no obvious canonical choice of coordinates on a torus, especially if it's not split. You know, when the torus is split, it looks like it's isomorphic. I mean, it's isomorphic to a bunch of copies of GM, and then you could say, okay, each GM comes with some X, right, and that you naturally think of. And so you could do this, but you know, what if your torus is not split? So the point is that there is always a sort of natural choice. So so suppose the chi1, chi-r are a basis of x star of t. So we're thinking of this as the characters defined over the algebraic closure, right? So over the algebraic closure, the torus splits, and you can choose a basis. It's not canonical, but that will not really affect the choice of the measure. So you could define, so you could kind of use these characters. So these characters give you an isomorphism that's defined over the algebraic closure. And you can ignore everything and say, fine, this will be my coordinates over the algebraic closure, and I just somehow pull back the measure. I don't care what I get. So you can define a volume form to be, roughly speaking, this. So let me quickly do an example to illustrate what is going on with this. By the way, I should say that this part owes much to the discussions with Bill Kesselman. So So this seems quite canonical in the sense because, actually, so let me do an example first and then discuss how canonical this is. So so the torus that corresponds to a quadratic extension, so torus in GL2 as usual, that corresponds to a quadratic extension. So suppose E, I'll write it as f adjoint square root of epsilon. So, and this epsilon, I mean, if the extension is unramified, this guy is a non-square unit, but this could be the uniformizer too. I mean, just some epsilon. Both cases could be considered. So then, you know, if I do something completely stupid, right? So the torus really, the f points of the torus look like this. It's x, x, y, epsilon, y, right? So this is, I'm just writing a matrix of multiplication by an element of x plus root epsilon y in the standard basis of the field. So I get this. So the characters, I could easily take, so I diagonalize this guy over the algebraic closure, and then I could use the usual fundamental characters, right, that send it to the first coordinate or the second coordinate. So I can have chi1 of this to be x plus root epsilon y. So I'm kind of doing a dumb calculation, but just to illustrate what's going on. So x minus root epsilon y. Okay, so, well, if I take the wedge product of these two, right, so what do I get? So, you know, I should put dx everywhere, dx, dy, you know, I should have done this, dx, dy. So the point is that, and so I'm just doing a very naive pullback of the measure of the dx over x dy over y measure using this. So if I do this, then this guy is paired to 0, this guy is paired to 0. I wind up with minus 2 root epsilon dx dy. And if I kind of think about this as pulling back the measure from GM, then I should divide by the determinant squared, right? So I should divide by chi1, chi2. Okay, and so so what does this give me? So the upshot of this is that, so what I get is I do get a differential form, but it is not necessarily have coefficients in the field, right? So it has coefficients in an extension of the field. So it's not a rational differential form, but it's a differential form. I could still take its absolute value if I wanted to. So I could actually work with this. So a better way to do this is, so this is what Wei does in his Adels and algebraic groups, is that, well, at least when you have, well, I'll write my torus, but he does it for a general variety. So if your torus comes by Wei restriction of scalars, well, I'll write this GM, right, because this is my situation. So in this situation, when you're dealing with restriction of scalars, the way Wei defines the pullback of a differential form is he puts in the discriminant of the field that you're extending scalars to into the picture. Yeah, I should take dx over x, right? So I should have, I mean, I just did this, but yeah, sorry, maybe I should say this. I kind of said this quickly, but I didn't write this. So dx over x, dy over y will then pull back to this 2 root epsilon minus dx dy over x squared minus epsilon. I just kind of ignored the denominator for a moment for this calculation, just computed the numerator. So the point is that this fellow just floats around and kind of messes the calculation up. And so if you look at Wei, when he does restriction of scalars, the discriminant, the square root of the discriminant of the field is built in. So so he does this everything in the global situation, and so the factor to the 1/2 times the dimension of the variety that you started with. So this is in the global field situation. Delta is the discriminant of the global field. So if you think of a torus that started with GM over a global field, extended scalars to a quadratic extension, so then delta is the discriminant of E over F. And so, so this discriminant gets built in. So if we think about it, then what happens at every place? So you see, well, at every place that's not ramified, this epsilon is actually a unit. So once you start integrating with respect to this measure, yes, maybe I'll write down the note. If E over F is unramified, and actually, and so this is nuance kind of starts. So, and the prime that we're dealing with is not 2. Right, so, or the prime V does not lie over 2 so that this 2 doesn't show up. Then the absolute value of 2 root epsilon periodically is 1. And so then it doesn't matter, actually, if we're doing anything or not. But this also means at that point, the absolute value of the global discriminant periodic is also 1, because unramified means that our P does not divide the discriminant. And so this 2 root epsilon, I mean, at 2, I don't even want to think about what's going on. I mean, that'll take another 5 lectures. So, so for this one, so matters when epsilon is, say, the uniformizer, or unit times the uniformizer, so when the extension is ramified. So in this situation, so that means that, but then this absolute value, then the p-adic absolute value of the discriminant is exactly this naive root epsilon that shows up inverse. So it's going to be 1 over square root of q, which is the same, I mean, secretly, I guess in this example, for simplicity, maybe let's think of f as qp. Sorry, I've started writing everything in terms of. So, which is exactly the absolute value of 2 root epsilon. Okay. No, that's fine. See. Okay, so the point is that when you build this factor into the definition itself of the pullback of the measure, so that looks like cheating, but you get a rational valued measure. I mean, a measure with rational, volume form with rational coefficients. And all the calculations with Tamagawa numbers, when they said that the Tamagawa number is preserved by restriction of scalars, happened with respect to this kind of definition of the pullback. So just built into the definition of pullback. So now there is a question to which I actually don't know the answer in full generality. So, what happens? So when T is a restriction of scalars generally, so what if T is not an induced torus? So, I mean, in general, for GLN, the exact same calculation happens with the same pullback. You see that every embedding plays a role. This discriminant gets compensated for. So when your torus is, for every torus in GLN, this works perfectly fine. What should this adjustment factor be exactly for some complicated torus which might sit in some, I don't know, symplectic group or something? I actually don't know a complete answer. Luckily, it seems that for some of the calculations that FLN do, that's not really needed. But for GLN, anyway, this works fine. Okay, and so all right, and so now, okay, but so with all these discussions, so we've got our form. So now we want to compute the volume of some maximal compact subgroup. So what's going on with that? So because remember, we've been discussing that kind of our way of, so we want to compare measures coming from differential forms with measures coming from normalizing it by just saying that this subgroup will have volume 1. So unlike the reductive group G, which kind of has a choice, unless it's GLN, in which case they're all conjugate of a maximal compact subgroup up to conjugacy, T has a unique maximal compact subgroup. So kind of the maximal compact subgroup. Is defined by the T in T of F such that the p-adic absolute value, again F is local, is 1 for all now chi from T to GM characters that are defined over F. So in our example, if T in SL2 is the norm 1 torus, which corresponds to E1, where E over F is a quadratic extension, right? Then it's already compact. There are no characters. And we have this T of F, its F points are precisely this norm 1 elements in E, and they're already compact. So then it's the whole torus. In GL2, for example, what we have is, so T of F is A cross, right? And in this situation, we have, so individual kind of fundamental characters, x plus minus root epsilon y are not defined over F, but their product is, we have the determinant. So, and the determinant generates all the set of all characters that are defined over F. So you get that T naught, the maximal compact subgroup. Oh yeah, I should really. I'm going to define it by T naught with a straight T. So T naught is the set of the ones where the determinant is a unit. And right, and so this is really, I mean, the picture to think of is, you know, if you think about things over R, right? So you can write something like C cross is the R points of the restriction of scalars from C to R. Oh, sorry, of GM. What did I write? This is a very difficult time to lecture when you come from the west coast of America. So, okay. So, yeah, so you have this, and so what we're doing here is it's a norm 1 torus times the positive reals, right? And so you're just kind of removing the positive reals, so you get a compact subgroup that way. So, all right. So, anyways, so this is our maximal compact subgroup. Of course, there is another complication here. Actually, before I say anything about complications, let me just finish computing this. So, what's the volume of this T naught with respect to our measure? So in it, let's incorporate. Well, actually, you know what? I'm going to not incorporate the discriminant because I don't know what it should be in general. So I'm just going to have this non-rational measure, whatever it happens to be. If it has a square root of Q, it'll have a square root of Q. So this is just pullback. So I'll just write it as honest pullback. Of kind of dx over x to the r from gm to the r, okay? So by honest, I mean that I have not tweaked it by any factors. So if we do that, so then what we are getting is, so then what we're doing is we're computing the following. So it will be the absolute value of this 2 root epsilon that kind of floats around if we had times an integral over what? Over the units of dx dy over xy. The xy doesn't matter because we're integrating over units. And so what we're doing really now is we can use the trick that I discussed at the end of the previous hour, which is to compute this volume. We just count the points on the reduction mod p. And so, well, let's do this. So this is, so this factor is either 1, so everywhere somehow the place that I'm working with does not divide 2. So, so this factor is 1 if E is unramified, and 1 over root Q if E is ramified. Okay, so we remember this. And now this guy is 1 over Q squared times the number of points on the reduction of the units of E mod its uniformizer. So this we will get to, this will be then, you know, so when E is unramified, then the uniformizer is the same old P that we started with, and we get the number of points in FQ squared, right? So this is going to be Q squared minus 1 if E is unramified. And Well, on the other hand, if E is ramified, let's do a little exercise here. So we want X minus, I'm going to just write it for QP, okay, just for simplicity. So you're trying to solve the equation X squared minus PY squared is a unit. And we're trying to see what happens to the, we reduce. So for this to work, of course, all you have to do is you have to have X mod P to be, basically X has to be a unit. And Y can be anything. So if you count the number of reductions mod P of such things, you will get, well, sorry, I mean, I'm skipping P, I'm confusing P's and Q's, but I hope that doesn't cause much confusion. So this is the general answer. I'm just doing an example over QP to illustrate the situation. So what you get is Q minus 1, that counts the reductions of X, and Q, that counts the reductions of Y, because Y could be whatever you want. And so this is if E is ramified. All right. And so the final answer is that the volume of this T naught with respect to this measure d omega is the following. I'm going to write cases which will be a bit more than what we just had. So it's going to be, I'll write it this way, Q minus 1 times Q plus 1 over Q if E over F unramified. Q minus 1 over Q times, well, Q over Q, which is 1. If A over F is ramified, times 1 over root Q. So that's the nasty thing that was there in front. I'll make it blue. I'll make myself blue in the process as well. So, all right. So then, and finally, I kind of forgot about the split torus in this discussion, but if my torus was split, then there was nothing much to do, right? So its volume would have been just, it was honestly just the volume of GM squared, right? So I'll have Q minus 1 over Q squared if T was split. Okay? But this is the time for questions. We will see these cases again, so this should start looking somewhat familiar, remind us of some things we've seen before. Questions? Okay, so, all right, so then the point of it is that, well, one can actually write this. Yeah, maybe I'll just say the punchline because I don't have a huge amount of time. Right, so, yeah, okay. So the point is, let's write it this way. So we can write it as 1 minus 1 over Q times 1 minus chi E of, sorry, that's not, sorry, I'm not doing a good job of this. Okay, I'll write this down and then try to explain what I mean by this. So all along, so if now, so, okay, so if this all came from a torus which was a restriction of scalars from E over maybe L, I don't know now so over a global field. And if we used Wei's way of pulling back measures, so Wei's pullback of measures, so that we would get rid of this guy, then what we're getting is precisely this chi E is the quadratic character so our situation then, what's V doing here? So my local field F is the completion of this global field that I started with at some V. Okay, so this is the quadratic character of the field E. Right, so this is the quadratic character, which is, so let's put it this way, chi E of V is 0 if V ramifies, -1 if V is inert, 1 if V is split in E. Right? And so, yeah, that's what we see. And so then, of course, it starts looking like if we were to take a product of these things, we will get an L value at 1 inverse associated to this quadratic character. And so we will see this theme again. So now some remarks about this. How general is this and what's going on? So the first remark is that, well, so this is kind of a very important remark. So we want to take a product over primes eventually. So what's going on here is that, well, so in GL2, so as we just discussed, our torus has this sort of GM component that survives right from the center. And so this would force this product to diverge because of these guys. So this way. So the factor in red this will cause the product to diverge. So we don't want that. So there is this endless process of adjusting things when they talk about Tomagawa measures. And so what you need is, so V introduces convergence factors. It's a little bit ironic when one talks about some Tomagawa number, which is ultimately a number, right? So everything is supposed to be canonical. I mean, otherwise it supposedly should adjust this all-important constant by something to make any other constant you want. And so everything is supposed to be very canonical, but in the process we make so many choices that it's sort of frustrating. So one of the choices that's been made is the choice of the convergence factors. So in the base book, everything goes with respect to a choice of convergence factors. These days it seems that the preferred choice of convergence factors is kind of the minimal thing you need to take out that came from GM, and then you preserve the rest of the information. So the way this is done officially and in general, so here we clearly see that this fellow came from GM, so we're just going to multiply by 1 over it, and this would be the convergence factor. So for us, it's going to be 1 over, well, I mean, sorry, I'll just write it this way. So it's going to be 1 minus 1 over QV inverse at each V. For us, I mean, this is the specific torus, which is the restriction of scalars from E to L of GM. So this is our torus that came from the quadratic extension. Now, what happens generally? So generally, you have, so remember where this fellow came from. So all of this trouble came from the difference between our torus T and the maximal compact subgroup that lives in it. And that came from the maximal compact subgroup was defined by wanting all rational characters to have absolute value 1. So this all trouble comes from rational characters of the torus that exist. So if you don't have any rational characters, you don't have this problem. And so what's going on, of course, is we have a representation of the Galois group. So again, F tries to stand for local field. So maybe, no, sorry, I cannot really get away with this. So okay, I'll do with the global field for now. So anyway, we have the Galois group acting on the characters of our torus. And this representation restricts to kind of a few copies of the trivial representation. So it acts trivially on the rational characters, right? That's what makes them rational. And so what you can do is you can, and so what this factor is, it's the Artin L factor of this trivial representation. So that's what you want to factor out, right? So the convergence factor is L of 1 sigma t inverse. So if you multiply by this, then this fellow will disappear. So, but then of course, if you do this, so when you do this at all primes, what you're left with, so this leaves, so this is a fine solution to the problem of non-convergence. That's exactly what you do. You basically kill the pole of this L function by just removing that part that corresponds to the trivial representation. But this leaves an annoying thing, so this leaves the residue of this L function at s equals 1. So when you're dealing with, so when working with T, which came from restriction of scalars of some quadratic extension of QP, then this residue will be 1 because you're just killing the zeta function. The residue of the zeta function is 1. So then this doesn't appear. So sigma t is this representation of the Galois group. So at every place you can think of the local Galois group on the rational part of the, so that's actually the occurrence of the, you can look at the whole representation, but then you only want to factor out the L function of the trivial part. So in our situation, so in most reasonable situations, well, you often assume that the torus you're dealing with is elliptic, so you're dealing with something an isotropic mode center. So this really is just going to be this one-dimensional trivial representation that comes from the characters of GM that sits in the center. And so basically, it's literally this factor that you have to kill. And if your base field is not Q, then you might pick up this regulator. So this residue is called the regulator, so that gives a factor of rho T. So I will write some more details about this in the notes. I mean, I don't want to spend time discussing this. It's not important for the future calculation. I'm just trying to say where this thing is coming from. It's because if you want to kill the obvious divergence of the product, you're paying a price, and the price is that the regulator comes in. So now, next thing. So unfortunately, that's not the end of the complication. So complication number 2 is that so we are seeing this kind of beautiful relation that we notice is that this volume of the maximal compact with respect to the differential form equals basically the value at 1 of an Artin L function, right? That's what we're seeing. So this can be easily, so maybe I'll do this in blue just to indicate what's going on. So this blue box can be interpreted as L of 1, again, yeah, maybe I can write it, I can still continue writing sigma t, I can just put trivial here. So this is the trivial part. And now I'm looking at the full representation. So this is the Artin L factor, and this continues to be the representation of, inverse, of the Galois group on the characters of T. And so this is very general, in fact, almost. So this is almost true in general. the almost part is itself very interesting. So what's going on is the following. So this is true for not always this maximal compact subgroup. So this is true is, well, for unramified cases, it doesn't matter. But if T is ramified, this is true if you replace T naught with a subgroup of finite index in it. So not a maximal compact subgroup, but a slightly smaller compact subgroup, which is the connected component. So just for experts, so you need the connected component of the Néron model of. So there is a somewhat canonical way to construct an integral model, meaning a thing that's the same over the field, but is actually defined over the integers and smooth over the ring of integers. And so, and it comes with many, it's for a torus, it's, unless it's really anisotropic, it's going to have infinitely many connected components. So you take the identity component. That identity component, it's OF points, or F points, doesn't matter. So its F points are a compact subgroup that's of finite index in this T naught. What this index is can be computed. So there's a beautiful paper by Ronnie Bitan. Again, I'll put references in the notes. Luckily, this index is not relevant for our specific calculation, but just be aware that when people take canonical, very often people in literature, especially Kothras, I think, refer to a canonical measure. They mean a canonical measure in the sense of Gross. By the way, Gross has a paper called Motive over Reductive Group. And there he constructs a similar representation so that its Artinel factor equals the volume of the group for any reductive group G. So that basically is equivalent to choosing a differential form or choosing a canonical model again. And so it's this whole spectrum of questions. And so when people say canonical measure, they refer to that. And so that, well, when you read Langlands or Scher or some other people, so then they actually talk about this subgroup. That generates a finite index problem. So for example, for SL2, there is a 2 that appears in here. So just be aware that the literature is not always the same on this. And so I'll put details of this in the notes. Okay, and finally, do I have any more complications that I want to whine about? Maybe not. Okay, yeah, I think this is it for complications. Good, any questions? All right, so the upshot of all of this is that something that we will see again in my lectures and something that we will see a lot in Ali's lectures is the appearance. So just notice one thing. So in fact, for Ali, I think it would be enough because he'll be working with GL2. He will switch very frequently between volumes of tori and L values, just a warning. And so this is where this is coming from. So we've done this computation. Okay. So, all right, so now I feel like I've at this point discussed at great lengths what this dg and dt are, and so now, so we have, so remember our orbital integral. So G mod the centralizer of gamma, which is this torus T of F of G inverse gamma G dg dt. So now we can say that, okay, we start, even if we start globally with the torus, say, then we will get this differential form obtained by pullback. So we have a differential form on G, we have a differential form on T, we have the quotient measure, we understand what that measure looks like. So that's kind of the hope. Okay, and so the next goal is we want to convert this to an integral with respect to a different radically different quotient measure. Yeah, I'm sorry, this is illegal, but this is the only way this lecture can proceed. So, sorry? I promise, yeah, the fine, yes. I promise not to spill anything. Thanks. I am a very bad example. So, okay, so, okay, so the situation is that, remember I promised that we were going to do something like Poisson summation of things like orbital integrals, and we're going to think of this orbital integral. So yeah, now remember that stable orbits are fibers of this Chevalier-Steinberg map from G to T split mod W. I don't know if this is a fair way to write this down, so maybe, this is maybe not such a good way of writing this, so I want to say, yeah, I think I gave a notation which was the center cross AG derived. Okay, this was our Steinberg-Hitchin base. And so there is a different way of giving it a quotient measure, right? So we have this is just kind of a naive picture. So this is the base, this is our G, this is the Chevalier map, right? And so for every point here, we have a stable orbit in G. And so then, so if you think of stable orbits as fibers of this map, then they should get a quotient measure of the measure on G by this measure on the affine space. So a quotient measure from this. So at this point, let's see what we already have. So we already have, so the measure on G is already normalized coming from a differential form. We made basically a single choice. Well, two choices. We made a choice of how to normalize a measure dx on the affine line, and we made a choice of a differential form on G. That's pretty harmless. And then, so the affine space below comes with the usual affine space measure. The only problem is that, so if you have this center, so then you give it the measure dx over x or whatever, the correct power of this. So you give an invariant measure on the center, and let's call this dA. This is just the usual affine space measure. Unfortunately, the caveat from the previous lecture on how to normalize the measure on the affine space applies. So if you had your favorite character of the Adels of the global field, then maybe you choose a self-dual measure on this affine space. That's what FLN do. And if you're me, you just have a naive one, which gives the maximal compact volume 1. So again, easy to adjust because this is just kind of a global constant, doesn't depend on the element. So, sorry? Oh yeah, so this is an invariant measure on, well, I mean, yeah, just, so if you don't have the center, then you just have kind of Lebesgue measure on this affine space. It's just an affine space. And so, again, it's a matter of normalizing the measure dx, right? And so if you normalize, once you've normalized dx, you know exactly what your measure on the affine space will be. And so it just comes from the same choice. So as I said, no, it won't be invariant anymore. No, I'm choosing a normal, Lebesgue invariant, translation invariant measure on the affine space. It's just an affine space. It's honestly, literally AN, right? There is a unique car measure on AN. No, I don't know. I'm not quite understanding. So I think I'm just, this thing, in my situations, I've been assuming that G derived is simply connected, right? So it really is literally an affine space. R-dimensional affine space. And because I already chose so I want to have additively invariant measure on this thing. So just the usual, dx1, dxn, that's all. And my dx is normalized according to preference. And so FLN has one preference, I have another preference, but it's not a big deal. It only, again, shifts everything by some global constant that comes from the global field and the character. Okay, so yeah, this is, and then on this, I think I kind of know where your question comes from, though, because there is some, So this matter, right? So here it seems so that they never really quite say, but I think what they have to take for everything to make sense is also normalize dx the same way as everywhere, and they have to take dx over x on every central, on every component of the center. Well, in our case, the center is just GM, so it's just this. Okay, so we're going to do this, and so now each orbit. So what does it mean to have a quotient measure in this situation? So now each orbit of an element gamma or stable orbit gets, so this is kind of, no, sorry, maybe that's not a good way to do it. So I'll write it as A equals C of gamma. Okay. So now each stable orbit gets a measure. I'm going to call this, I don't know, omega A or something to indicate that it's a differential form that depends on the image downstairs. Because now you see, so the measures on orbits, they're of course G invariant, but so they differ, say, so on each orbit, the measure would differ from this measure that I've already defined, this dg dt. It would differ by a constant, but this constant can now depend on the orbit, and that's exactly what happens. So, so this is kind of a quotient form. What I mean by this, so I can look at, there are two ways of doing this. So one can look at the decomposition of the tangent space of G. So maybe the tangent space at gamma of G, so it's tangent space to G at gamma. I mean, you know how integration on manifolds works, right? Everything is determined by forms living on the tangent space. So you have a decomposition of the tangent space to the orbit of gamma. I'll just write this approximately, and kind of a copy of the tangent space it's not A derived, it's AG derived. So you see what I mean. And so you have, I mean, more precisely, you have an exact sequence of vector spaces, and so you have a volume form. You have a volume form living here. You have a volume form living there, and so omega A wedge. What should I call this guy? I'm going to call this dA. So I'm going to just, so this is the affine space measure on AG derived cross Z. Sorry, I mean, I'll call this, so I'll call the whole thing affine space measure, okay, just so that I don't have to keep talking about the center. It's not really playing any role at the moment. So anyway, so I have the measure on the base. So this is just the measure on the Steinberg-Hitchin base that I've just defined. And this is the measure on G. And so what I need is omega G to be the wedge product of this omega A and the measure dA that lives on the affine space. All right, so that's one way of thinking about it. Another way of thinking about it is just to write down what happens for an integral if I integrate a function over some compact set. So another way of saying this is that for f in CC infinity of G, an integral of f of G dg over G should be, I should be able to write it as an integral over the Steinberg-Hitchin base. So integral on C inverse of A, dA, f, d omega A, right? That's what I'm doing. And I would like to leave this formula for comparison with Weil integration formula. So actually now I'm going to do, for simplicity, so that it actually fits into a lecture, I would want to compare it with the Weil integration formula. Right, oh yeah, so what I should say is that the current goal is, I'll never use the blue again. So, doesn't erase. So, okay, so the goal is to figure out the conversion factor between how does this omega A relate to dg dt. So remember this guy, so it only depended on the centralizer, right? Then for all elements gamma, it's kind of insensitive to this. As long as you're on the same torus, it doesn't matter. So this fellow will actually depend on gamma. So just kind of as a spoiler. Okay, and so to figure this out, so for now, let's do things, let's just go to the Lie algebra. So it's already, so basically that means that what I'm doing right now will work literally for gamma near the identity, otherwise we can just think of this as an analogy. So on the Lie algebra, so this is just basically because the calculation was measured as a calculation on the tangent spaces with differentials anyway. So hopefully this is a reasonable convincibility. But it's just because Chevalier map on the Lie algebra is a little bit easier to think about. But otherwise it's basically the same thing. So, well, recall Weil integration formula. So f is in CC infinity of g. So then the integral over g of f of y dy is the sum over tori up to conjugacy. 1 over the order of the Weil group of that particular torus, integral over t. I can write t or t regular, doesn't matter. D of x integral over g mod t. I'll write this down and explain what's going on in here. Okay. Right, so this is just a standard way of breaking down an integration over g into integrals over orbits, basically. So now, well, what is this based on? Oh yeah, so who is d of x? Sorry, I should have defined this guy. So this d of x is the Weil discriminant. And so let's write this down. So it's, so on the Lie algebra, d of x is the product of all roots. So another way, well, I guess the standard definition of this is that it's the determinant of add x restricted to the quotient space G mod T, right? The adjoint of x acts trivially, so T is the Lie algebra of the centralizer of x, right? So at the moment, I could integrate only over regular semi-simple elements here, then the centralizer is again a torus. The adjoint of x acts trivially on T, so if you want the determinant to mean anything and not be 0, then you really want to compute it on G mod T. And so you get that. And it turns out to be the product of the roots. And so why this formula works is kind of for the following reason. It's, if you look at, sorry? Oh, right. Thank you, yes. This will never end. So this dx is the usual, I mean, I guess affine space measure. So the Lie algebra is luckily just affine spaces. So this both are, so this is affine space measure on T. And so this is just additive Lebesgue measure, and again, so this is kind of affine space measure. they have to come from compatible normalizations of the measure on the affine line. But by now, I've just assumed that they're fixed one. And so then everything will be compatible. So on G. So these are just usual. I mean, luckily, so as I said, for the Lie algebra, life is a little bit simpler. And so, okay. So, and then, yeah, this dg dt is the honest, this is literally the same dg dt, right? Because this is the integration on G mod t. So we've just discussed that. Also, notice that here things are a little bit insensitive to the choice of. So I mean, yeah, you can kind of see how both things scale if you rescale the measure on G or the measure on T. I don't want to get into this right now because I only have 5 minutes. So I mean, let's put it this way: there exists a compatible normalization of measures that makes this work, and I think they are really just as long as they've come from the same normalization of just the measure on the line, then you're fine. Oh yeah. What I should have said the dg and dy are linked by the exponential map, having to be measure preserving in the neighborhood of the identity. Oh yeah. This will never end. Okay, so yeah. So, anyways, so what this works. So the reason for this, the real reason for why this works, is that if you look at the map from G mod t times G to G, which sends Gx to G inverse xg, right? So the Jacobian of this map is the discriminant. Sorry? Oh, times t. Yeah, thanks. Yeah, sorry. Yeah, otherwise the dimensions are wrong. So, right, so the Jacobian. Okay, this is something you kind of have to believe, and Kottwitz explains this really well in the notes. And so, okay, right. So I still have 2 minutes. So yeah, okay. So let's look at basically. Let's look at how this compares to that. So suppose everything here was over the Lie algebra, just so that I can compare it more easily, right? So then let's see what's going on in here. So the claim is that basically here I'm integrating over the fiber of the Chevalier map if you squint really hard, right? So it's like I'm integrating on the orbit in both situations inside. Now what's going on the outside? So basically here I want to be, so basically what we want to do is we want to replace this. What we want is T mod W. I mean, regular doesn't matter. I mean, I could integrate over the whole thing, right? So in principle, because, so the point is that so remember what we discussed last time, that T split mod W is up to a set of measure 0, which does not come from regular semi-simple elements here, is a disjoint union of images of tori up to conjugacy, right? And so, so this sum, so let's put it this way, images of tori. On each of the images, over each of these, the map from T to T split mod W is a WT to 1 map. So that would take care of this factor. So this starts looking very much like the integral. So my point is that I would like to claim that this, roughly speaking, looks very much like the integral over T split mod W, except there is a little bit of a problem. Remember this map from T to T mod W, it was not something easy. It was you had to compute coefficients of the characteristic polynomial. So this map will have a Jacobian of its own. So luckily the Jacobian of this has been computed. And this Jacobian is product over positive roots of alpha of x up to a constant that depends only on the torus. And so, well, which really, I mean, so when you're working with the Lie algebra, what you have is that, so this looks like, yeah, so summing it up, yeah, I want to kind of stuff it into the last minute, so just so I don't have to talk about it next lecture. Summing it up, everything kind of looks like it could match if, so what we have basically is, okay, I'm going to write it down. So what we have is something like this, just with respect to measures. So 1 over W over the split torus, let's say, over T is split. So then WT is the full Weil group. So the Weil integration formula looks like this. Right? And then if I were to try and match it with this kind of formula, I will get 1 over the order of W, d omega A, dA. And this dA, so this is the measure on T mod W. This fellow is d of x to the 1/2, just because I only want positive roots. I don't want all dx. Okay, and so then these guys cancel. I only get 1/2. And so the upshot of this kind of fudge of a calculation is that it looks like we're getting that dg dt times d of x to the 1/2 is this d omega A. So for the Lie algebra, you get that. So for the group, you have to be a bit more careful about what you're doing with this discriminant. And okay, so far I've only said what I do over the split torus. What happens over the non-split torus? So you're picking up this constant that depends on the torus, and you have to be really careful about how you've normalized the measure on the torus, and we come back to the same circular story, which, again, so I'm glad to be saved from that by the bell, but this is getting into the notes, so that cost me a lot of pain at some point in my life, so I did eventually figure this out. So if you actually have the measures, the way we've done it, coming from the characters, then this constant is always going to be 1. And so that's what FLN claim, and it seems to actually work. Okay, thanks. And yeah, so I think, so basically the 2 things to remember from this whole mess is that first, the measures on tori are interesting and give us L factors. And second, when you want to convert to the integration over the Hitchin base, the square root of the discriminant comes up. And the rest is going to be somehow sucked into volumes of tori, and since we have a volume of the centralizer anyway, we can reshuffle those factors later. And that's what will happen next class. Thanks. Late. Yeah, so there are 2. Yeah. So in fact, I mean, it should have probably been done. So I just wanted to kind of point out the similarity with the Weil integration formula, but in reality, what one should do is just do an honest calculation on the tangent spaces and just compute the Jacobian of this map, but it kind of comes in 2 steps anyway, because you have to first conjugate your torus to T and then go down to T mod W. And so both of these calculations show up anyway, and I just thought that since most people hopefully have seen Weil integration formula, I just thought you could use it to explain it quickly rather than do a computation. And I actually have examples of just differentiating things in the notes, so that will be there. But I had a professor back in Russia who said never differentiate in public, so I decided to kind of follow that rule because it's